Let's start with the interaction of light and matter. Next, we will continue with the physics of Raman effects and the physics of atomic vibrations in matter. Let's conclude with the Raman experiment technique and some examples of experiments. The Raman phenomenon is the result of the interaction of light and matter. When light encounters matter, a lot of things can happen. Some light is absorbed and transformed into other forms of energy. Light that is not absorbed by matter can be reflected of it or can be transmitted through it. Some of the absorbed energy is converted into electromagnetic radiation as luminescence. It should be noted that luminescence often appears as disturbing factor in Raman experiments. A small portion of the incident radiation is scattered by matter. Next, we will look at the properties of this radiation. Scattered radiation includes light with unchanged frequency and light whose frequency is both increased and decreased. Radiation with an unchanged frequency is the relay scattering. Radiation with a frequency different from the frequency of the laser is Raman scattering. How can this phenomenon be explained? The description of the phenomena can be done using both classical physics and quantum mechanics. Let's start with the classical physics model. The incident radiation polarizes the molecule and induces an electric dipole in it. The polarizability of a molecule depends on the distance between the atoms. For atomic vibration with small amplitudes, we can perform mathematical calculation, which will result in formula with three terms. An electric dipole oscillates at three frequencies. As now, an oscillating dipole emits electromagnetic radiation. The first term corresponds to radiation with unchanged frequency. This is the Rayleigh scattering. The frequency of the second term is reduced by the molecular vibration frequency. The frequency of the third term is increased by the molecular vibration frequency. The second and third terms correspond to Stokes and anti-Stokes scattering, respectively. In the case of the single vibration, the spectrum of scattered light should look like this. As can be understood from the above, the position of Raman bands depends on the frequency of laser radiation. Therefore, the so-called Raman scale is used in Raman spectroscopy. In it, the coordinate axis is directed in the direction of decreasing frequency of electromagnetic radiation, and origin of the coordinates corresponds to the frequency of laser radiation. On the Raman scale, the position of the bands corresponds to the vibration frequencies of the molecules. But most importantly, the position of the bands does not depend on the frequency of the laser used in the experiment. Reciprocal centimeters as a unit of frequency are widely used in vibrational spectroscopy. What is it? Frequency in vibrational spectroscopy is defined as the reciprocal of wavelength. A frequency defined in this way is called a wave number. Here, as an example, you see the Raman spectrum of carbon tetrachloride molecule. The beginning of the Raman scale is centered on the laser frequency value. In the center of the spectrum is a relay scatter peak at the laser wavelength. This peak is millions of times more intense than the Raman scatter. This determines a certain constructive difference between Raman spectrometers and luminescence spectrometers. The relay scatter peak is normally blocked by a notch or edge filter. In practice, Raman spectrometers are most often designed to measure the Stokes spectrum. Symmetrically placed on each side of the relay peak are the 4 Stokes and 4 anti-Stokes peaks, correspond to the Raman active vibration of carbon tetrachloride. The Raman spectrum was first obtained by Raman in 1928. The Raman spectrum of benzene was obtained. The light source was mercury lamp, and the spectrum was recorded on photographic plate. Raman bands appear as bands next to bands of a mercury lamp. Raman scattering is caused by the motion of atoms in molecules and crystals. Therefore, it is important for us to become familiar with the vibrations of molecules and crystal lattices. At molecular oscillations, the model is a two-atom molecule. The atomic masses are M1 and M2. The atoms are connected by the spring with the first constant K. Mathematical calculations give a formula for the square of the oscillation frequency. The square oscillation frequency is proportional to the force constant and inversely proportional to the reduced mass. The vibration frequencies of polyatomic molecules also depend on the structure of the molecule. Only two atom molecules have one vibrational mode. Polyatomic molecules will contain many vibrational modes. For nonlinear molecules with n atoms, the number of vibrational modes is given by 3n minus 6. For linear molecules, 3n minus 5. Not all vibrational modes can be detected using Raman spectroscopy. Vibrational mode is Raman active when the molecular polarizability changes during the vibration. We return again to the Raman spectrum of the carbon tetrachloride molecule. 4 bands are visible in Raman spectrum of carbon tetrachloride. The calculation of the number of vibrations gives 9 vibrations. Why such a difference? The analysis of vibrational symmetry helps to solve this problem. The carbon tetrachloride molecule has tetrahedral symmetry. Symmetry analysis is performed using the irreducible representation table of the point symmetry group. It turns out that there are vibrations with the same frequencies. This is determined by the symmetry of the molecule. The E-symmetry mode corresponds to 2 vibrations with the same frequency, and the T2 mode corresponds to 3 vibrations with the same frequency. As a result, 1A, 1E and 2T2 symmetry modes correspond to 9 vibrations of the molecule. The symmetry of a molecule also determines the vibrational activity in Raman and infrared spectra. As can be seen in the table, all oscillations are active in Raman spectra, but only T2 modes are active in infrared spectra. Carbon tetrachloride has one of the simplest Raman spectra, but the same principle applies for all samples. Raman spectroscopy is used to measure the unique vibration fingerprint of the sample. From that information, chemical, structural, and physical properties can be determined. This slide shows the effect of symmetry reducing on vibration spectra. In the case of molecule dichlormethane, there should be 9 bonds in the Raman spectra. There are 8 active vibrations in the infrared spectra. 1 vibration remains inactive. All 9 vibrations have different frequencies. In the case of solids, chemical bonds connect a huge number of atoms. There are approximately 10 to the 23rd power of atoms in 1 cubic centimeter of crystal. This corresponds to a huge amount of vibrations. Which vibrations can we see in Raman spectra? We choose a simple 2-atom linear chain model. Mathematical calculations give a formula for the vibrations frequency, but here is a new parameter k, called the wave vector. In crystals, the vibrations of atoms have a wave shape. For this model crystal, 2 vibrations are produced for each wave vector. The wave vector k characterizes the length of these waves. As the value of the wave vector changes continuously, the vibration frequencies also change continuously. Vibration frequencies are usually graphically represented as function of the wave vector. The vibrations of our linear chain are characterized by graph consisting of 2 curves. The vibrations of one-dimensional crystal with n atoms in its crystal cell are characterized by the following n curves. In the case of real crystals, vibrational waves propagate in 3-dimensional space. These directions are characterized by the brilliant zone. The slide shows the crystal lattice structure and brilliant zone of silicon. The slide also shows the dispersion curves of vibrations in different symmetric directions of the brilliant zone. Each wave vector has 3n vibrations. The point and translation symmetry of the crystal lattice dictates that only vibrations with k equals 0 are active in the Raman and infrared spectra. These are long-wave vibrations. Since the frequency of the 3 acoustic vibrations, if k equals 0, are equal to 0, then 3n minus 3 vibrations can be seen in the Raman spectra. For silicon crystal, n equals 2, and the 3 optical vibrations have the same frequencies, so silicon has only 1 Raman band. Now we will continue with the technical setup of the Raman experiment. The monochromator, laser and sample chamber are the main components of a Raman spectrometer. Laser line filter offers maximum transmission of laser emission, while eliminate noisy spontaneous emission. The laser beam is focused on the sample. The lens focuses the scattered radiation onto the entry slit of the monochromator. The notch filter is used to suppress relay radiation. In a monochromator, grating splits the light into wavelengths. which is projected onto the detector plane. CC detectors are currently widely used. The most commonly used optical geometries are 90 degrees and 180 degrees. 180 degrees or backscattering optical geometry is used in Raman spectrometers with microscope. By choosing one of two polarizations of the laser and Raman scattering, it is possible to measure Raman scattering for 4 different polarizations. The optical scheme of the micro-Raman experiment is shown in this slide. The microscope is equipped with XYZ stage which allow for mapping experiments. Our Raman spectrometer is technically more complex. Its main component is 3 monochromators connected in tandem. You can see the principal optical scheme here. We can work using a single monochromator. In this case, the intensity of Raman signal is the highest. This scheme is also the most commonly used in experiments. In more complex experiments, all 3 monochromators are used. The use of 3 monochromators is important for experiments with high spectral resolution, up to 0.1 reciprocal centimeter, or measurements up to 5 reciprocal centimeter from the laser line. There is wide range of Raman spectrometers on the market. Companies offer spectrometers that are optimized for different client needs. In this slide we see several Raman spectrometers. Here you see popular Renishaw spectrometer and Trivista spectrometer, which is similar to our Raman spectrometer. At the bottom of the slide you see Horiba brand spectrometers. Here is high-resolution spectrometer, a spectrometer with an AFM unit, and a mini spectrometer with Raman fiber probe. Many analyses can be performed with portable Raman spectrometers. They are convenient to use in nature, at customs offices, and elsewhere. For special analysis, combined instruments are used to simultaneously measure Raman spectra and some other physical properties. We will now look at some examples of applications of Raman spectroscopy. Perovskite-like YAP crystallizes in an orthorhombically distorted perovskite structure. Crystals with ideal perovskite structure do not have Raman active vibrations. As the crystal lattice deforms, its symmetry decreases. This leads to the activation of lattice vibration in the Raman spectra. The YAP crystal has a totally 24 active Raman vibrations in its Raman spectra. They correspond to 4 different symmetries. Therefore, by properly choosing the experimental geometry, we can obtain a Raman spectrum corresponding to vibrations of one particular symmetry. We obtain AG symmetry vibration spectra if the polarization of the laser beam and Raman scattering are parallel and coincide with one of the crystallographic axes of the crystal. You see the spectra with polarizations parallel to the 3 crystallographic axes on the slide. The intensities of the bands in the spectra vary greatly. This corresponds to the theoretically expected 7 modes. In the case of YAP crystal, we have been successful and have obtained the Raman bands of all 7 AG symmetry vibrations. This is often not the case. Here you see the Raman spectrum of a good graphite crystal. The second Raman spectrum is for graphite with crystal lattice defects. The intensity of band D depends on the concentration of defects in the crystal lattice. As the defect concentration increases, the size of the non-defective areas decreases. A relationship has been found between the size of the defect-free area and the ratio of the G and D band intensities. In the example shown in the slide, the size of the non-defective particles is 175 angstroms. In the case of anatase, as the crystal size decreases, the Raman band broadens and shifts towards higher frequencies. A different picture is observed in the case of silicon nanoparticles. The Raman band also broadens but shifts to lower frequency range. The band shift also depends on the shape of the nanoparticles. Surface-enhanced Raman scattering is surface-sensitive technique that enhanced Raman scattering by molecules adsorbed on rough metal surface. A large amplification factor has been achieved in experiments, which means the technique may detect single molecules. Electromagnetic theory and chemical theory are often used to explain cells. Raman mapping of a sample area provides information about the chemical and physical differences across a sample. Raman imaging can be performed across a two-dimensional plane or three-dimensional volume. Raman imaging allows for material identification, quantitative analysis, the detection of strain and crystallinity, layer number in quantum materials. Raman images are acquired using a confocal Raman microscope. Many substances can exist in multiple states. The slide shows how the Raman spectrum changes in different states of iridium oxide. The structure of iridium oxide changes from crystalline to nanocrystalline and then to amorphous. Here the structure depends on the synthesis conditions. The use of the group frequency method in the analysis of Raman spectra is widespread. Group frequencies are vibrations that are associated with certain functional group. It is possible to identify a functional group of a molecule by comparing its vibration frequency on Raman spectrum to Raman stored data bank. Raman spectroscopy is increasingly used in many specific studies, like in geology. Raman spectra help identify minerals. Non-destructive analysis of works of art. Raman spectroscopy helps archaeologists. Also helps in living cell research in biology. In conclusion, what information can we obtain from the frequency and shape of Raman bands? Each chemical substance has its own characteristic set of Raman bands. The formation of the crystal lattice leads to shift of the Raman bands. The band polarization characterizes the symmetry and orientation of the crystal. The width of the Raman bands characterizes the quality of the crystal lattice. The relative intensity of the bands contains information about the concentration of chemicals.